For decades, modern space exploration has demanded massive, multi-billion-dollar investments. To leave Earth's gravity, nations build machines the size of skyscrapers, supported by infrastructure that drains national budgets. This chart compares the harsh financial realities of lunar programs. A single launch of NASA's Space Launch System costs an estimated $4.1 billion. In stark contrast, the Indian Space Research Organization achieved an entire historic lunar landing with the Chandrayaan-3 mission for approximately $75 million. That is less than the production budget of a mid-tier Hollywood science fiction movie. But the moon's south pole does not check a spacecraft's bank account before it arrives. The physical environment treats a $90 billion program and a $75 million program with the exact same lethal indifference. When you parallel park a car, you have sensors and time to adjust. Landing on the moon means approaching a rocky, pitch-black surface at over 6,000 kilometers per hour. There is no atmospheric drag to slow you down, no GPS to guide you, and a 3-second communication delay that prevents anyone on Earth from helping in real time. Miscalculate your velocity by a fraction of a percent, and you add to a growing junkyard of expensive hardware. In the past decade, highly funded lunar landing attempts from Russia, Israel, and Japan have all ended in catastrophic crashes. India reached this milestone through a ruthless philosophy of frugal innovation. They replaced expensive, sprawling designs with a high-performing mechanical simplicity that redefined aerospace economics. The highest cost of any space mission is the rocket required to leave Earth. To keep costs low, ISRO developed and manufactured nearly every piece of their hardware in-house, completely eliminating expensive foreign supplier markups. NASA's traditional Apollo and Artemis architectures rely on massive heavy-lift rockets. These launch vehicles possess enough raw thrust to push a payload directly to the moon in a matter of days. India's engineers relied on their existing domestic workhorse, the LVM-3 rocket. It is highly reliable, but it lacks the lifting capacity required to shoot a lunar lander straight across the solar system. This orbital map illustrates their workaround. Unable to afford raw horsepower, ISRO traded time for fuel. They fired the spacecraft's engine in highly calculated bursts, raising its orbit into gradually expanding concentric ellipses around Earth. The spacecraft spent 40 days gradually gathering momentum from Earth's gravity before perfectly slingshotting into the moon's gravitational pull. In September 2019, India's previous attempt at a lunar landing shattered on the surface. With the entire nation watching, the Chandrayaan-2 lander was a mere 2.1 kilometers above the moon when its central fifth engine fired with slightly too much thrust. The sudden speed increase overwhelmed the onboard guidance computer, resulting in an uncontrolled impact at roughly 53 meters per second. ISRO engineers collected the flight data and mapped out every conceivable way the new lander could crash. They adopted a failure-based design philosophy, identifying single points of failure and eliminating them entirely. Looking at the design of the Chandrayaan-3 lander, you can see the immediate result of this process. They completely removed the central fifth engine that caused the 2019 crash, relying exclusively on 4 corner engines to manage the descent. They also installed a Laser Doppler Velocimeter. This complex sensor fires precise light beams at the surface to measure the spacecraft's exact speed in 3 directions, acting as an independent failsafe if the other navigation instruments disagree. The engineering team reinforced the landing legs to survive a heavier impact, upgraded the onboard processor to correct its angle 2.5 times faster, and expanded the acceptable landing zone from a tiny square to a massive rectangular grid. To shave millions off the budget, Chandrayaan-3 didn't even launch with a new communications relay. Instead, it linked up with a still-orbiting satellite left behind by the crashed 2019 mission. A tight budget forced ISRO to scrutinize every gram of mass and every line of code, resulting in a hyper-optimized machine built exclusively to survive. When Chandrayaan-3 dropped below 30 kilometers in altitude, it was completely on its own. Because of the communication lag to Earth, the engineers in mission control could only watch as the spacecraft initiated its fully autonomous descent. During the rough braking phase, all 4 engines fired at maximum thrust, burning heavily to kill horizontal speed and bring it into a vertical drop. As it descended to 850 meters, the craft hovered. The onboard cameras and velocity sensors rapidly fused data, scanning the rugged topography below to identify a flat, hazard-free patch of regolith before committing to the final drop. In those final seconds of freefall, budgets and geopolitics ceased to matter. The spacecraft's survival depended entirely on the flawless execution of ISRO's navigation algorithms. On August 23rd, the engines shut down, and the lander made contact. Almost immediately, the rover rolled onto the surface, detecting sulfur and mapping thermal gradients in the lunar regolith, the layer of loose dust and rock on the surface, gathering high-value scientific data on a massive discount. This technical success paved the way for India to sign the Artemis Accords in 2023. This agreement moves India into a strategic partnership with the United States, where their high-efficiency robotic missions provide critical precursor data for NASA's larger crewed explorations. ISRO demonstrated that reaching deep space targets no longer requires an endless supply of capital. Disciplined mission scoping allows high-stakes science to be achieved within the constraints of a sustainable budget. Reaching the surface of the moon requires extreme precision and absolute fiscal discipline. Chandrayaan-3 demonstrated exactly how far smart engineering can go.